All right, so it's time now to look at applying concepts on page 531. Number 1, what is the difference between the current generated in a wire when the wire is moved up through a horizontal magnetic field and the current generated when the wire is moved down? So what it's saying is you have a horizontal magnetic field like this, and you have a wire that's running like this way. So you're going to move it up and you're going to move it down. And what is the difference? Well, assuming conventional current, because that happens to be the hand I have free, if you move it up, the current's going to be into the page, and if you move it down, the current's going to come out of the page. So the difference is the direction that the current is going to flow. It's going to flow in opposite directions, and that's true whether it's electron current or a conventional current. Number 2, we actually already did. Substitute the units to show that EMF is measured in volts. So I just put it, I assigned it there again just in case you wanted to go back and see if you could do it on your own, but you do have it in your notes now. Number 3, if the strength of a magnetic field is fixed, in what 3 ways can you vary the size of the EMF? So let's imagine we have a magnetic field strength that is set, and we want to change the EMF, thus changing the current that's flowing in the wire. What could we do? What are the 3 things actually that we can do to change that? Well, 1 is you could change the length of the wire in the field. 2, you could change the speed with which you're moving. And 3, you could change the orientation or the angle. So really think of the equation EMF is equal to BLV sine theta. And it's saying B is fixed. What can you change to make EMF bigger? Well, you can change the other 3 things. Okay? Number 4, when a wire is moved through a magnetic field, resistance of the closed circuit affects what? Sorry, let me double check that. What did it say? When a wire is moved through a magnetic field, resistance of the closed circuit affects, it should affect the current only. Okay? Because if you think about a wire is moved through a magnetic field like this wire, the resistance, like the EMF is the voltage, and that's going to be affected by the size, the strength of the field, the length of the wire, the speed you're moving it, and the angle. That's the voltage. Voltage is equal to IR. So the question is saying, what will the resistance affect? It's going to affect the I. The V is being determined, the EMF is being determined by the BLV sine theta. So the R is going to affect only the current there. The V will also affect the current, but changing the R won't change the V. It'll just change the current. The V is set by BLV sine theta. That was number 4. Number 5, as Logan slows his bike, what happens to the EMF produced by his bike generator? Now, I know that we didn't talk about generators yet, that they're coming, but if you can imagine when you're pedaling a bike, it's the faster you're moving, the bigger the V, and so as it slows down, if you're creating an EMF, as it slows down, the EMF is going to get smaller. Okay? A hand crank generator, we need to talk about generators, is dropped, but I knew you could do these with common sense. If you drop a hand crank generator, weakening the permanent magnet, how does this affect the speed with which the generator must be cranked to keep the same EMF? If you do something to weaken the field and you want the same EMF, well, then you're going to have to move it faster, right, to make up for the fact that B is smaller. Okay, so that's 5 and 6. I think I skipped 7, but I did ask you to do 8. So 8 is this picture. A wire segment is moved horizontally between the poles of a magnet, as shown in this figure. What is the direction of the induced current? So the poles of the magnet are going that way, but the wire's being moved this way too. Sine theta is 0. There's going to be no current generated here, right? You have to move the wire in such a way to actually cut the field lines. Number 9, Martha makes an electromagnet by winding wire around a large nail. I think I asked you 9, yeah. If she connects the magnet to the battery, is the current larger just after she makes the connection connection or several tenths of seconds after the connection is made? Or is it the same? It's going to be biggest right after she hooks it up. You have to think about the Lenz's law piece there. Remember, Lenz's law always causes current to flow to protest the change. So when she hooks it up, a large current will flow. But then remember, in Lenz's law, we don't like this large current, so we're going to create a current to flow opposite it. It's called a back EMF to try to cancel out what's being created here. Did I ask you 10? I think so. A wire segment is moving down through the poles in 2514. What is the direction of the current? This is 2514. The wire's moving down. Your book always thinks conventional current. So with your right hand, put your thumb down, put your fingers from north to south. The current should be flowing out this way, which is actually what they're showing you with the little dot there. I don't think I asked you to do anything until you got to 16. Steve is moving a loop of wire down through a magnetic field as shown in not this picture, the one on the next page. Will the induced current move to the right or left in the wire segment? So 2516 is this one, I think. No, not this one. This one, right? So now I have to flip back and see what the question said. Steve is moving a loop of wire down. So you're moving it down. Field is going from north to south. You're moving it down. So the current should come out this way. I know it says used with problem 2, but it also is used with that back one. So the current should be coming from like inside the page to the out, or I guess that would be like left to right. As soon as the wire is moved in the field, a current appears. Thus, the wire segment is a current-carrying wire located in a magnetic field. A force must act on that wire. What will be the direction of the force acting on the wire due to the induced current? So the current is coming out. The field is going this way. So it should be experiencing a force upward, right? Field in the fingers in the direction of the field. The current, we said, was flowing from inside the page to outside. The force comes out of the palm of your hand. It should be acting upward on this loop. All right, 17. I think my book, which is older than yours, has Steve in both of these questions, but I think your book has a girl here, but I don't remember who the girl's name is. Guess it's, trying to give equal opportunity to the genders. A physics instructor drops a magnet through a copper pipe. It's shown in the picture on the next page. The magnet falls very slowly, and the class concludes there must be some force opposing gravity. What is the direction of the current induced by the pipe as the falling magnet on the south pole, induced in the pipe by the falling magnet if the south pole is towards the bottom? So this is the south pole here, and the magnet's falling down, but the pipe doesn't like the fact that there's a strong field coming down. So it wants to try to stop the slowing down of this magnet. And so it's going to create a current in the pipe itself that's going to set itself up in such a way to try to oppose this south. In other words, to flow in such a way to create a south pole that would then oppose here. So a south pole would be your hand going like this, because remember your thumb is the north. So your fingers would curl around this way, and that would create a south pole facing up, which would slow this guy from falling down. Now, wouldn't it be cool if we could see this? I have the best toy in the world. So when you come back to class, I will show you this. It's called Lenz's Law apparatus. And then we'll come back and talk about the rest of this question, because I do know that it's probably confusing. So it says the induced current produces a magnetic field. What is the direction? The south is going to be on the top, so the field lines will go into the south. Okay. And how does the field reduce the acceleration? Well, it repels the other magnet coming down and slows it down. But I'll show you this. You'll love it. Woo-hoo. You won't be able to sleep tonight thinking about watching it. All right, those are all your homework questions.